Hi, so today talking about the photoelectric effect. So, photoelectric effect. Okay, so imagine you have a piece of material here. It could be anything. Usually it's a metal, so I'm just going to use a metal. And you have a laser. So this laser is going to shoot a light beam. That's what lasers are. And what's going to happen to the metal is that the metal contains a sea of electrons, right? And the electrons, when hit by light contains energy. The electrons, when given enough energy, the electrons are going to be ejected. So, electron going to be injected. And this is the photoelectric effect. So, about this light beam. The energy of this light beam is proportional to its frequency, to the frequency of the light. Light behaves as waves. So, as a particle and waves. So, the energy of laser is equal to this constant called Planck's constant times the frequency of light. That's the energy given to these electrons. So the question is, do these electrons have energy of h times f here? The answer is no. Why? Because they are bounded to the nucleus. Electrons are bounded to the nucleus, and when given enough energy, they'll be ejected. So what is this energy? So, of course, so let's back up a bit. So the electrons here, I'll use purple. The electrons here, they only have kinetic energy. They only have energy of 1/2 mv squared. So, and they are bounded to a potential, essentially. And they are bounded by a work function. So, the equation here, the energy equation here, is that the electron, they have 1/2 mv squared. They're given h times f amount of energy from the light beam, but you have to subtract that from the potential, basically what's called a work function. And each metal has its own unique work function. So it only works, the electron will only be ejected if this is positive. If this is positive, the electrons will be positive, will contain kinetic energy and will be ejected. Otherwise, the electrons will still be bounded to its nucleus or still be in its lattice. So, another thing about this equation, h times f, is that the units are quite interesting, especially for the Planck constant, which will be used later. So, this constant, h, the units for it are quite interesting. So, the units. So, let's rearrange this top equation. Let's rearrange. So, we know that E of laser equals to h times f. So, that means h equals E over f. So it has units of energy over the units of frequency. What are the units of energy? The units of energy are essentially the units of the kinetic energy, 1/2 mv squared here. So 1/2 mv squared, we're only considering the units, so it has units m, and it has units length squared over time squared. I dropped the 1/2 because we're only considering units. And the frequency, as we call it, f equals 1 over t. T is the time of the period, which is given by units of time. So it has units of 1 over t. 1 over t. Okay. So let's simplify. So h, the units of h, has units of m L squared t. And let's rearrange this a bit more. So the units of h equals to the units kilograms and length over time times the length. So notice here that this is the unit for velocity. And as you recall, this equation, which is angular momentum, was r cross p, it also has the same units because, for example, it's going to be mv r sine theta, where r is the length, have units of length, v have units of velocity, and m, of course, mass. So Planck's constant here has units of angular momentum, which is quite important for spins, like spin 1/2, which I'll get to maybe later someday. So this is the photoelectric effect and Planck's constant. See you guys in the next video.